Good morning, everyone. We are Group 5. I am Ankit with my teammate Mithalpati Jil Patel and Vaibhav Shukla are here to present our topic thermomechanical interaction between TSV and active devices quantifying a stress-induced performance degradation in transistor due to TSV. So let's begin. So let's move to the second slide. Today, chips are no longer flat. We now stack multiple semiconductor dies vertically. This is what we call 3D integrated circuit or 3D IC. And the technology that makes it vertical stacking possible is the through silicon via or TSV. So the biggest question is, what is the TSV? A TSV is copper filled vertical hole that is drilled straight through a silicon die. You can think of it as a highway that carries electrical signal directly from top die to the bottom die by passing all horizontal wiring. A single TSV can be anywhere from 2 to 50 micrometer in a diameter with an aspect ratio up to 20:1. TSV are used everywhere in today's world because of high computing power and less time requirement, means fast calculation. So why do we need 3D IC with TSV? Because today conventional chips are hitting their limit. With TSV. We get much higher integration density, more transistor per square millimeter. Interconnection becomes shorter, so latency and power drop significantly. We can also mix logic, memory, RF all in one package, what we call heterogeneous integration. This is what exactly shown in the figure here. We are moving towards 2D to 3D.
Hello everyone, I'm Zil Patel and I am presenting the previous work which has been done regarding this topic. So before the TSV technology was introduced, several interconnect methods were used in semiconductor packaging. The earliest method was wire bonding, where gold or aluminum wire connected to the die package lead frame. However, the long wire length caused high inductance and resistance, leading to the signal delay and limited bandwidth. Also, the vertical stacking was not possible. Then come the flip chip or C4 bumping in the 1990s. In this method, the die was flipped and connected directly to the substrate using the solder bumps. This reduced interconnect length and improved I/O density compared to wire bonding. However, it was still fundamentally a 2D integration method and limited by bumpage, typically around 100 micrometers. Multi-chip modules and system-in-package placed multiple chips side by side on a common substrate. While this improved the system integration, it increased the footprint and did not provide true vertical stacking. Package on package allowed stacking of package, but only peripheral solder walls were used for the connection, so bandwidth remained limited. The real breakthrough come with TSVs, which enable true 3D vertical integration with very short interconnect length, high bandwidth, low power pad bit, and reduced latency. On the right side timeline, we see that the stress effect were first noticed in 1990s with shallow trench isolation. Later, strained silicon technology showed that the stress can intentionally improve transistor performance. When TSVs were introduced in early 2000, mechanical effects were not initially considered. Over the time, researchers began modeling TSV-induced stress, defining keep-out zone, and recently even using stress-aware EDA tools and machine learning for mitigation. Now let's understand the physical origin of thermomechanical stress in TSV-based 3D ICs. So during the fabrication, the chip undergoes annealing at around 300 to 400 degrees Celsius. At high temperature, both copper TSVs and silicon expand and stress generation is minimum. The problem arises during the cooling. Copper has coefficient of thermal expansion of about 70 parts per million per Kelvin, whereas the silicon has only about 2.3. This means copper expand and contract nearby around the 7 times that of the silicon. So when the structure cools down during the room temperature, copper tries to shrink more than silicon. However, the surrounding silicon restricts its contraction. As a result, tensile radial stress develops in the silicon around the TSV. The stress is maximum at the TSV edge and gradually decreases with the distance, approximately following a 1 over r square decay behavior. Typical residual stress values for narrow TSV can range from 150 to 200 megapascal, and after annealing, stress can increase up to 600 to 700 megapascals. The stress magnitude depends on TSV diameter, pitch aspect ratio, and linear materials. This thermomechanical stress directly affects nearby transistor, which is why stress modeling is a critical for reliable 3D IC design.
Thermomechanical stress and device impact. So now we'll talk about causes of thermomechanical stress. So main cause is CT mismatch between silicon and copper. Uh, as you can see, there is a 7 times difference between CT of copper and silicon. So when copper shrinks from 250 to 300 degrees Celsius to room temperature, This will lead to residual tensile stresses up to 700 megapascal at the edges of silicon wafer. So this will lead to silicon crystal lattice deformations, and this will affect mobility shifts, threshold voltage, and drain currents. Also, this will lead to copper fatigue and interfacial crackings. So we can see some formulas for that. So first two formulas talk about total stresses. There is superposition of bending stresses due to warping of silicon wafer and also shrinkage of copper. The third equation is like change in yield stress due to grain size effect, and grain like decrease in grain size. So there's that talks about the microstructural point of view. And the fourth equation is mobility change due to like piezoresistive effect, where pi is piezoresistive constant and s is stress generated in particular directions. So this all will lead to timing failures and yield loss and reliability degradations in our silicon um, like wafer. So now we will talk about literature review. So first paper we selected was this ASME 2019 paper. This talks about the FEA technique to see the effect of TSV stresses on nanoscale transistors. So modeling both TSV and transistor in single model is very computationally expensive because TSV are in micrometer sizes and the transistor is in a nanometer size. So what we can do is um, we can create this global local submodeling. So we will find out stresses in particular area in global model, and we will remodel the transistor and use that stresses values in the local model. As this is the finding, as you can see, the stresses are increasing with the TSV diameter. Also, the carrier mobility gain is decreasing with the TSV diameter for nanoscale transistors. This is the equation we will use primarily from this paper for the carrier mobility loss.
So let's move to the second paper. These copper wires are incredibly useful, but they comes with the hidden problem. Copper and silicon expand at very different rate when they are heated up. Copper expands nearly 7 times more than the silicon. So every time the chip heated up during manufacturing and then cools back, the copper inside TSV tries to sink much more than silicon around it, and this creates a huge mechanical stress. This MRS Bulletin 2015 by Liu et al. Asks very important question: exactly how bad is this stress, where it appear, and how does copper internal grain structure effective? To answer this, author used a combination of advanced experiment, X-ray diffraction, atomic force microscopy, electron microscopy, wafer curvature measurement alongside semi-analytical stress model. Their key findings are that the stress near the top surface of TSV is far more complex than the standard formulas prediction. The copper grain grows and permanently deformed during thermal cycle, and copper can physically extrude out of TSV holes, potentially damaging layer built on the top. Now let's move to the figures. So look at this color map. They show the stress that build up in silicon right along the TSV when chips cool down. Red means high stress, blue means low or even compressive stress. The left map shows stress pushing upward and downward called axial stress. The middle shows stress pushing outward in all direction, that is radial stress, and the right map shows twisting or shearing stress near the top edge of TSV. The key message is near the surface of silicon, the stress pattern is far more complex and dangerous than what simple 2D calculation predict, and this is what can cause copper silicon interference to crack and peel apart. So next figure here, we can see actual TSV test sample, a piece of silicon with copper wire arranged in a grid about 40 micrometer wide and 50 micrometer apart. On the right, you can see what happened when you heat it up. The vapor went upward, curving negatively. When it's cooled back, it bent on other way, that is positive curvature. The graph shows its behavior measured at 4 different peak temperature. 100 degree, 200 degree, 300 degree, and 400 degree Celsius. Now, how heating is non-linear and messy, but cooling is almost perfectly straight. The difference tells us that plastic deformation, permanent damage is happening inside the copper during heating. And as the copper plastically deform more and more, it locks in the higher stress at room temperature even after each thermal cycle. This colorful strip image are microscope map of copper grain structure inside a TSV. Each color represents different crystal grain orientation from left to right. You can see how the grain becomes fewer and larger as the temperature increases from room temperature through 100, 200, 300 and all the way to 400 degrees Celsius. The bar chart on the right quantifies this average grain size grows from 0.9 micrometer as received state nearly to 1.2 micrometer after cycling to 400 degrees Celsius. Why does it matter? Large grain means lower yield strength. The copper becomes softer and more prone to permanent deformation under TSV stress. This directly explains why processing temperature makes the stress situation worse. These three panel shows X-ray technique reveal about the damage inside the TSV in panel A. The color map shows how silicon crystal lattice is slightly tilting or bending near the copper wire. The orange and the blue at the top is indicated the silicon is being pushed and pulled by the copper thermal expansion. Panel B shows copper itself. The peak width of X-ray peak is widest near the top of the wire shown in red, meaning the copper has undergone local plastic deformation. It has been permanently squeezed and distorted there. Panel C is show X-ray diffraction peak shape in 2D and 3D. Instead of sharp clean spike, the peak is broad and spread out, which is directly a fingerprint of internal stress and deformation inside the individual copper grain. This is the last set of graphs shows fascinating and very practical problem. Copper physically extrude or pump out of the top of TSV. Graph is shows the height of profile measured by atomic force microscopy. The pink curve after the 400 degree cycling shows copper is sticking out up to 175 nanometer above the silicon surface. Graph B and C compared two TSV size 5 into 50 micrometer and 10 into 100 micrometer and show how extrusion occur at different annealing temperature. The key finding is annealing low temperature around 200 degrees Celsius minimize extrusion. At very high temperature, a smaller TSV extrude much less, confirming that the grain near the top of the wire controls this effect. If copper extrusion is not controlled, it physically damages layer built up on the top of it and causing real device failure.
The first research paper is shown in this page is proposed by Tan et al. In 2026. This research paper focused on a critical gap in TSV modeling. The problem shown by this research paper is that conventional methods treat copper as simple uniform material, but this paper proves that copper is anisotropic, meaning its behavior depends upon its internal grains. The study shows that ignoring these grains leads to a 50% error in stress prediction. The solution and result given by this paper is that by using EBSD data, real microstructure images, the author found that grain orientation is the key, especially grain orientation in 100 direction shows the least fatigue damage. Controlling this during manufacturing can make TSV much more reliable. There is a image in the slide. The image show tells us about that the red zone indicate maximum stress at copper silicon interface. Unlike simple models, the stress here is non-uniform because of the different grain bodies. In the last, this is exactly where keep out zone is most affected and where transistors are likely to fail.
Now, I will briefly summarize the chip package co-analysis of thermomechanical stress in TSV-based 3D ICs. So what happened is during the fabrication, copper annealing and solder deflow occur at high temperature where the structure is assumed to be stress-free. However, during the cooling, the room temperature, significant residual stress developed due to the coefficient of thermal expansion mismatch between copper, silicon, and solder. You can say that the solder microbump and underfield has a relatively higher thermal expansion coefficient compared to the silicon. So that due to this cooling induced stresses dominate reliability concern in 3D ICs. When the multiple dies are stacked, global thermomechanical bending creates a vertical stress gradient. The bottom die experiences the highest von Mises stress because it is closest to the package bump and furthest from the natural axis. Stress decreases towards the upper dies. To efficiently analyze this, the paper proposed the LVLS method, which is also called as lateral and vertical line superposition method, which reconstruct the total stress by linearly superimposing stress contribution from TSVs, microbumps, and package bumps. This approach achieves very small error compared to the full finite element simulation while significantly reducing computational cost. The main conclusion of this paper is that the thermomechanical stress in 3D ICs is a system level problem influenced by geometry, stacking configuration, alignment, and material properties, also requiring cheap package co-design. The research gap addressed by this work is that earlier studies mainly focus on isolated TSV stress, whereas this paper provide a scalable full chip analysis framework that captures both lateral and vertical stress interaction efficiently.
Now let's discuss the six key solutions to manage and improve TSV reliability. The first one is annular trench TSVs. The first solution is structural. Instead of a solid copper cylinder, we use a ring-shaped copper design. This reduces the total volume of copper, which directly lowers the thermal expansion and overall stress on silicon. The second one is using tungsten as an alternative material. We are looking at tungsten because its coefficient of thermal expansion is much closer to silicon compared to copper. Using tungsten reduces the mismatch right from the material level. The third one is optimized or barrier layers. We use thin layers like titanium nitride because between the copper and silicon. These act as a material cushions or buffer, absorbing some of the stress before it reaches the transistors. The fourth one is stress aware placement. This is a design level solution. Instead of just leaving empty space, we place critical cells in beneficial stress zones. This clever placement can improve timing performance by 21.6%. The fifth solution is microstructure and grain orientation. Based on the latest research by Tan et al., we found that controlling the internal copper grains is vital. If we orient the grain in 100 direction, the TSV become much more resistant to fatigue damage during the thermal cycle. And the last solution is machine learning tool, that is stream. Finally, to speed up the design process, we use aluminum-based tool like stream. These can predict stress hotspot instantly, allowing us to fix reliability issues during the runtime of the design phase.
So propose methodology and action plan. So this is our action plan for the rest of the semester. So phase 1 will be analytical baseline and FEA setup. So we will use Lami's equation to calculate the stresses for the verification of our FEA model. We will create some basic FEA model. Phase 2 automated data generation or parametric sweep. So we will use ANSYS Design Explorer to run automated parametric sweep. We will vary three parameters to generate dataset of 50 to 100 points. Phase 3 machine learning surrogate model. We will take that data that we have generated and we will make some regression model as random forest or some other model. Phase 4. Phase 4. So from our ML model, we can mm, predict the device degradation and fast KOZ, that is capped out zone. So we will apply our formula delta mu by mu naught to predict the carrier mobility loss. So also we can optimize our model using different method. To conclude our presentation, we can say that one, TSV stress is unavoidable due to high CT mismatch between copper and silicon. Number two, transistors are directly impacted. Uh, there will be high carrier mobility loss in transistors. Number three, analytical models are insufficient. Uh, Lamy solutions will give huge errors. So full FEA models are important. Number four, smart placement solves KOZ problem. Uh, in ICCAD 2010 paper, we can see that smart placement will reduce like 21.6% timing errors. Future is stress exploiting design. So now annular trace TSVs, ML runtime tools like Stream and Cilium Germanium co-design will be defining the next generation solutions. Um, Below you can see the references for our presentation.